Welcome to Chem Help ASAP. In this video, we'll identify acidic hydrogens. There will be two different types of questions. The first four ask you to pick the most acidic hydrogen. The last four ask you to pick which molecule is more acidic. Go to the description of this video to find links to printable copies of these problems as well as printable solutions. This video also contains links to other videos that might help you with this type of material. Let's try to quickly dash through some ideas of acid and base equilibria. So for a typical acid-base equilibrium, and let's assume our base is water, which it may or may not be. Here's our equilibrium. So when determining this equilibrium, the magnitude to which it lies to the right, the equilibrium constant, really the most useful thing to look at is this anion, which is our conjugate base. The more stable that anion, the weaker that conjugate base is, and therefore the stronger the acid will be. So to understand the acidity of a proton, I find it most useful to look at the conjugate base, which is often where our charge is, and then to evaluate how good or bad that charge is, how stable or unstable that charge is. What are the ideas we use to think about stability? Well, we think about the size of the atom that bears the charge, the electronegativity of the atom that bears a charge. There's resonance. There is induction, and other ideas, hyperconjugation, hybridization. That's pretty much the gamut. So we'll use those ideas as we look at these anions. Now, not all acid-base reactions look just like this. In some of them, the molecule is already protonated and has a positive charge. And this can react with water, or some base, to make a neutral conjugate base plus H3O+. So here's our conjugate base. Now, if you're used to thinking about acid-base reactions the way I say, you're going to look at the conjugate base and say, oh man, I don't have a charge to evaluate. Sometimes you have to look over at the parent acid. If the parent acid has a positive charge, then the conjugate base will be neutral. So you look at your acid for the charge. How do we evaluate that acid? Well, we use the exact same ideas. We say, well, what's the size of the atom that bears the charge? Is there any resonance? Are there inductive effects? Exact same thoughts. And of course, in this case, if the charge is more stable, then we get direct information on the acid. The acid will be a weaker acid. More stable, less reactive, weaker acid. So this is kind of a framework for how I tend to look at acid-base reactions. And now let's see some problems where we can determine whether the acid, one proton is more acidic than the other. Okay, here's our molecule in the upper left. Our job is to predict which of these hydrogens is the most acidic. So I'm going to draw the conjugate base as we deprotonate different hydrogens. There are four different hydrogens in this molecule. We have the NHs, we have those CHs, we have those other CHs, and then we have the OH. So I'll do A, and let's do then maybe C and D. B we'll see is not a very good option. So here's deprotonating A. We'll get an N-, and if we do C, we get a C-, and if we deprotonate at D, we get an O-. Okay, which one of these is most stable? Well, as we look across this, here we're looking at N-, C-, and O-. We're really looking at a periodic table trend. We're moving across the periodic table from C to N to O, O is the most electronegative. Therefore, it is the best at stabilizing that negative charge. So the O minus form would be the most stable of the different anions we've shown, and therefore D, that's the most acidic proton, and we've drawn the conjugate base to the far right. Now, one thing I want to bring up about C has something going for it. There is an inductive effect. That oxygen would help stabilize that C minus, but let's not get carried away. It's still a C minus. It's still really unstable. So you can make this super unstable thing a little bit less unstable, but the C is far worse than A, which is the N minus, and way, way, way worse than the O minus. So there's our first problem. Okay, problem 2. Here's our compound in the upper left. So we have actually just 3 different hydrogens to remove. We could remove the OH, labeled A, one of those CHs, labeled B, or another OH. So for A, I won't put in all the lone pairs, but I'll put in those. There's an O minus. It's not a great O minus. It's localized, has no resonance. We could deprotonate on carbon and get that C minus. And then for C, last but not least, we get that O minus. So I'm going to start with C because that's actually our answer. What's great about C is that we can do resonance and delocalize that negative charge onto another oxygen. So here we have resonance, and resonance is always a good thing. Going back to A, we have no resonance. This is now a localized O minus. Now B is not as terrible as it looks. I'd say, yikes, it's a C minus. Are you kidding me? Well, through resonance, we can push that electron density up onto the oxygen. And now that doesn't look so terrible. But let's not kid ourselves. It's not as good as C, in which we can draw 2 resonance forms, both of which have an O minus. So C is definitely the most acidic hydrogen in this particular structure. Problem number 3 looks very much like problem number 1. We have our structure in the upper left. Let's go ahead and label some hydrogens. Just like in problem 1, I did A, C, and D. We'll do the same thing here. So we need to figure out which one's most acidic. We need to draw these different conjugate bases and decide which one is the most stable anion. So let's pull off the proton off of that sulfur. For A, B ups, let's not do B, let's do C. We should have left that as B. Okay. There's our anion, our conjugate base from deprotonating at carbon C. And then finally, let's deprotonate on oxygen D. Well, here in this case, it's not a straight electronegativity answer because we have sulfur. Sulfur is a third row element. It's a big atom, and therefore, when we put a negative charge on it, it's a very diffuse negative charge. So for size reasons, the sulfur anion is more stable than the oxygen anion. And you might say, but oxygen's more electronegative. You're right, it is more electronegative. But when you're in a vertical periodic table trend, size is what's more important. So size is the main factor. There's no reason to even discuss electronegativity here. Now again, C is the third place because it's C minus, which is terribly unstable. Now we could try to make a case that there's an inductive effect, and there is one, but it's nowhere near as important as the electronegativity we saw with oxygen, or more importantly, the size effect of sulfur. So sulfur is our most acidic hydrogen in this model. This SH is the most acidic hydrogen. Problem 4. Okay, we have 2 OHs. We'll label those A, and then we'll just talk about one of these CHs. They're all bad, but we'll show one just as a representative example. So for structure, if we deprotonate the hydrogen on oxygen A, we get this anion. This is going to have resonance. And, you know, carboxylic acids. There's a reason why they call them carboxylic acids. They're acidic. So that is a nice, stable anion, and we can draw a second good resonance form. So this is looking really good because of resonance. Resonance, okay. Now let's look at B. B is an oxygen that will deprotonate. And there is our O minus. And look at this. B has its own merits. We can draw some resonance. And we can delocalize that charge right into the benzene ring. That's not terrible. But notice what we're having to do is we're having to draw these resonance forms that make carbanions. So even though we do have resonance, it's just not as good. It's supposed to be a C. Resonance, and it's because we're drawing these carbanions. Now we could continue drawing more resonance forms, but overall we have another problem. We are disrupting this aromatic ring, which we may or may not have talked about in your classes yet. But those aren't great resonance forms. So the C minus is not as good. A is looking better and better. Let's see what answer C has to show us. We could draw this carbanion. And that is completely localized, and it's a carbanion. So this one's terrible. Okay, so the winner here is the OHA, and that H is the most acidic hydrogen in this molecule because it forms the most stable conjugate base. We are now in the second group of hydrogen, or second group of problems, where we are now comparing two different molecules. So the compound on the left, I'll draw the full Lewis structure. It looks like this. If we draw the conjugate base, it looks like that. The right-hand structure, or Lewis structure, looks like so, and here would be the conjugate base. Now you might say, these don't look that different. They're both carbanions, and neither of them really has any good resonance to discuss. So they look more the same than they look different. However, what is different about these is their hybridization. The structure on the right, this is an sp hybridized carbanion. This is an sp2 hybridized carbanion. And here is what people rationalize as a difference. So that sp hybrid is kind of a short, squatty orbital because it has very little p character. The sp2 is not like it's a mile long, but it is more elongated. And I'm going to try to exaggerate it in this picture because it has more p character. It's sp2 instead of sp. The p character, it gives you more elongation, and so therefore the electron density in the sp2 case is further from the nucleus. Over in the sp, it's closer to the nucleus because it's not such a long orbital. Therefore, this negative charge, it likes being held more tightly to the positively charged nucleus. Therefore, this conjugate base is more stable. It's a weaker base. And this structure is the stronger acid. So our explanation here is hybridization. All right, problem 6. I love problem 6. These are great examples. Okay, the structure on the left, let's draw its conjugate base. There we go, a localized nitrogen anion. And the structure on the right, let's do the same. Let's draw the conjugate base. Again, a localized nitrogen anion, so the identity of the atom is the same, so electronegativity is not the answer. The size of the atom is the same, so it's not a size effect. There's no resonance in either of them. So these again look very similar. Well, the only difference is this oxygen in the top of the ring on the right-hand structure. So the answer has to do with that oxygen. And that this is going to form a polarized bond. Well, when you start talking about polarized sigma bonds, you are in the realm of inductive effects. And the way you describe this is that this carbon, let's get our better cursor, this carbon is slightly plus, this carbon is also barely slightly plus, and that partial plus helps stabilize this N minus. The same is occurring on the other side. This carbon's got a little bit of electron deficiency because of that oxygen at the top of the ring. So this N minus is a little more stable. The more stable that N minus is, the weaker the base this is, and therefore the stronger the structure on the right is as an acid. So this is the stronger acid over this structure. The answer is the compound to the right, and it's because of the inductive effect, this polarization of the sigma bonds in the molecule. Problem number 7. Let's draw our conjugate base of the right-hand structure. We're going to pull off one of these NH's. Not going to touch the CH's. And then in the right-hand structure, again, we're going to pull off one of these NH's. Not the CH's. Well, in this case, we have a double bond in the right-hand structure. And double bonds often mean you have resonance. And that's exactly what we have here. This fits the description for when we often encounter resonance. So the N minus makes a carbon-nitrogen double bond. And we can slide that electron density right up on oxygen. So now we have another resonance form. The structure on the left is just a localized N minus, no resonance at all. So the right-hand structure is the more acidic structure, and it's more acidic because the conjugate base is stabilized by resonance. If the conjugate base is more stable, less basic, that means the parent structure is a stronger acid. So the stronger acid is on the right for reasons of resonance. Problem number 8. This is a great question, I think. So we have these two structures. One, we need to figure out where we're going to deprotonate these things. As it turns out, this position is the best place for deprotonation. We'll pull off one of those CH's. Now, problem 8, we have two sides to this ketone. So we can get resonance into the carbonyl on both of them. But this one is going to turn out to be better, and we'll see why. So let's draw. Let's give a little more space. Tell you what, let's abbreviate this ring as phenyl to give us more space. So if we deprotonate this carbon, we now have a double bond next door, and we can delocalize that negative charge into the oxygen. The oxygen is a much better home for all that electron density. And now this anion, this conjugate base, doesn't look so bad. We can actually delocalize that C minus over to oxygen and get an O minus. Now let's look at the right-hand structure, and I will draw out the full benzene ring for this one. If we deprotonate on the right-hand side of the carbonyl, we can then do this exact same resonance and we get this structure. Now there's something else we can do. We could also delocalize some of this electron density into this benzene ring. Now to do that, we have to mess with the double bonds of the benzene ring, and that is not really a good thing. But even if it's just a little bit good, it's something that the left-hand structure cannot do in its resonance form. We can't delocalize into the benzene ring. So this right-hand structure has a little bit more up its sleeve in terms of electron density delocalization than the left-hand structure. So for problem 8, the right-hand structure is more stable, and it's not that it has resonance, because both structures have resonance, but the right-hand structure simply has more resonance. So we'll go with the right-hand structure as being somewhat more acidic than the left. I hope you found this video helpful. Please subscribe, like, or leave a comment, or leave a question. In particular, I'd love to hear if there are other problems you'd like to see. Thank you for watching, and remember that links to printable copies of these problems and solutions are in the video description. Take care.